Good afternoon, my name is Scott Greenwald, and I will be presenting on applying a Gaussian kernel to a mean shift algorithm, as well as applying a linear prediction filter to the mean shift algorithm to determine if the processing speed is improved, as well as the tracking efficiency. So why is tracking so important? For military purposes, it could mean life or death for the warfighter. It also could mean whether or not we are targeting the enemy or a civilian themselves. Being able to track the correct person, vehicle, missile, if it's being launched at us, is critical for mission success and carrying out what our mission truly is. But tracking is also used for civilian purposes as well. We can use tracking for locating suspects of a crime, whether or not they're in a street, for example, where there's a camera. We can target which individual in the field of view is the criminal himself, and then be able to tell the police where to locate this target. It's also used in sports, for example, where if we want to determine how far a baseball was hit on a home run, tracking algorithms are used in order to track X amount of frames from the moment the ball was hit to determine the velocity and the spin on the ball, and then they are able to predict how far the ball will actually travel. So tracking algorithms are actually used on a daily basis. So there are three different main types of tracking algorithms: point, kernel, and silhouette tracking. Point tracking is more of a feature-based track where we designate a specific point on a target or a point of interest, for example, and frame to frame locate that point of interest and then follow that point throughout the video itself. Kernel-based tracking is more of a general tracking algorithm that looks at the target's motion. So we're able to target a much larger sample rather than a specific point, look frame to frame on how much that target itself has moved, and then follow it based on the motion rather than a specific point. Silhouette tracking is similar to kernel, where it's motion-based, but it's for more advanced objects. So they are looking more for edges, for example, and follow the edge and the pattern of the edge throughout the frames themselves. For this research, I decided to use a kernel-based algorithm called the mean shift algorithm. And how this tracking algorithm works is it determines the probability density function of our parson window and then shifts to that local mean, hence mean shift algorithm. How this works is essentially every image has a histogram, and we will find the densest region of that histogram and shift our window to that dense region. And this process is iterative until we converge on the local mean itself. So to give a visual representation of this is all a hypothetical example, but this is an example of what an image would look like. This black oval represents where the current track is, while the red represents the actual local mean of the image itself. The blue vector is then calculated in order to shift from our current location to the local mean. And as I stated, this process is iterative. For this research, I decided to make it capped off at 5 iterations per frame in order to keep the processing moving along so that we don't hit any infinite loops or slow down the tracking process itself. So I've been talking about parson windows and what they are, but to be able to visualize what they are, we decided to present in this research a flat and a Gaussian kernel. The flat being the most general type of kernel itself. It's defined by this current piecewise function, and as you can see, every pixel is either represented by a 1 or a 0. If we took a square, for example, and drew a circle within the square, every pixel within that circle would be weighted equally, while everything outside would be neglected. Now this could be a problem for real-life situations because targets that a user is going to designate will include some background pixels or some noise of the image, and these pixels will be incorporated into the statistics of the histogram and be weighted all evenly, which could throw off the track of the algorithm. I also decided to use a Gaussian kernel, which essentially will take the middle of the window itself, weight those pixels the most, and as we gradually move to the outside of the window, eventually get down to where those pixels do not count. into these statistics. Now this is very important because, as I was saying, if we designate a target and there are background pixels, or there's something blocking the image itself, such as a vehicle moving behind a tree, those pixels may not be weighted as much and the track will be able to continue. So going to the actual mean shift algorithm itself and declaring what that mean shift vector is, we follow this equation right here. And essentially, this equation is going to take the ratio of the pixel values within the local parson window, and then essentially take the ratio of those values by the weighting factor depending on which kernel you're using, whether flat or Gaussian or any other kernel, and then subtract out the initial local mean. That way we get a nice x and y dimension of where the current mean is compared to the actual local mean, and then we shift by that value itself. For this research, I also wanted to work with a linear prediction filter to improve the processing and tracking of the mean shift algorithm itself. So I decided to use a basic Kalman filter. And how this works is I take the 4 previous frames and essentially see how the motion of the track has moved over those frames to get a nice predicted starting location on the current frame. The way the mean shift algorithm works is on the current frame, we will start at the location of where the target was on the previous frame. With a Kalman filter, we will not use that last frame location. Instead, we will predict where it will be on this current frame. That way we are much closer to the actual location, and the statistics are going to be more accurate. So to give a quick block diagram of how the Kalman filter works is, essentially I'll take the 4th previous frame, subtract it from the 3rd previous frame, and do the same between the 3rd and 2nd. So right here we'll have an x and y dimension for every pixel, and then another x and y dimension here. We will then average the two out because it is a linear prediction filter, and essentially apply it by adding it to the current starting location. Now, the averaged x and y locations could either be plus or minus, depending on which direction of motion they are going to be using. And when we apply it to the starting location, we will then get a nice predicted location. This block over here should be a much better representation of where the target will be on the current frame when compared to the non-Kalman filter starting location. So in order to present this topic, I wanted to build a graphical user interface, or GUI, in MATLAB where I'd be able to visually watch the video, which is presented in this white box over here, and be able to easily adjust which type of tracking algorithm I use, which I can do up here. I can decide whether or not to use a flat or a Gaussian kernel, and whether or not to use the Kalman or non-Kalman filter. The other important aspect of this type of tracking algorithm is the image itself. So I added in a couple image processing options down here where I can adjust the contrast, the sharpening, or the brightness of the image as well. So while adding a lot of contrast may not be visually appealing to the human eye, for a computer it actually may be more beneficial because it'll allow a greater contrast between the target and the background itself. So now I'd like to give just a quick live demonstration of how the code works and the GUI itself. So I run this code, I will get my GUI that will pop up, and I'll open up an example of a video that I recorded with just a car driving through a parking lot. And to get a good track, I will apply a Gaussian window, and I'll save off the video just as a test file. So now if I designate a target of the frame of this car right here, I'll draw a square rectangle around it. And as you can see, I do have some pixels on the brake light and some on the windows over here, but due to the nature and the math behind the Gaussian window, it will not be influenced nearly as much as the frame. So if I hit run, the video will record, and as you can see, the window follows that frame of the car very well. It's able to move along with the car without too much jitter, But as we get behind the trees, as you can see, it's kind of bouncing around now, and eventually it loses track completely. This is because the car is passing behind a tree, and as the number of pixels of the tree, the branches and the leaves get in the way, then we will lose the statistics of the car itself. Now, for example, if I reload this same video and I apply a Gaussian window with the Kalman filter itself and apply essentially the same window and run the code, you can see that it does jump around. It did see that there was some movement in the Y direction, but it's able to follow the car based on the same contrast. And as it passes behind the trees, it's able to follow it much greater. It's actually gone significantly further along than without the Kalman filter. And even when the car is almost visually gone, it was able to follow it. Until it's completely non-visible where it is right now, it was able to follow it pretty completely. And that's due to the prediction itself. It knows that we're moving in the negative X direction and the positive Y direction. And even though it might not be able to see the car that well, on the start of the algorithm when we define that vector, we are able to already be at the location of where the vehicle will be itself. So because this takes some time to run the code and showing the examples, I've pre-recorded several other examples of the mean shift algorithm itself as well. So this is an example of just a person walking across the street, and I designated the entire person himself because that's what in real life situations we'd be doing. And I'm going to be applying a flat window for this. And as you can see, it doesn't do a very good job. It follows him slightly in the beginning, it moves laterally, but essentially it's tracking the ground. And that's because the majority of the pixels for the flat window itself are the background. So now if we apply a Kalman filter with this, it'll actually make it worse because it sees the motion of moving downwards and to the right a little bit. It's going to continue that path, and because the contrast of the ground itself is the same, it continues with the path until it follows off the screen. Now if we apply just a standard Gaussian window to this same video, we're able to follow the person pretty well. It bounces up at the top a little bit because it sees a lot of the extra ground over there once we get past the foliage, and we do essentially lose the track at the end of the video a little bit due to some of the statistics, but you can see that it follows the target much better. So now if we apply the same Gaussian window but with the Kalman filter this time, we are able to follow the track the same way. It jumps up a little bit right around the end as well, but it is able to come back down to the target and get back on target compared to the human at the end of the video, unlike the non-filtered video itself. So just for a couple other examples, here's another video of a car. I'm applying just the Gaussian window, and I'm trying to track the headlights this time. And as you can see, without any jitter, I'm able to follow the car itself. Now the reason why this video is different compared to the human walking across the street is the background pixels for every frame of the car is the same. It's always the black portion or the black paint of the vehicle. While the human walking across the street, you see the pavement, you see some of the foliage, the light pole. So this type of track where the target itself, the entire target itself is not being designated, but a portion of it, it's able to follow that much greater. Here's another example of myself just going through a golfing swing, and I'm applying a Gaussian window with the Kalman filter, but I'm not going to apply any image processing. This is exactly what was recorded from my camera itself. Now I'm trying to track my non-glove hand, and as you can see, as we followed all the way up in my backswing, I'm able to follow my hand pretty well. But as I come down and the speed of my hand greatly increases, along with this building over here, the track gets lost because of similarities between contrast. So if I apply the same Gaussian window with the Kalman filter, but I apply image processing where I've greatly increased the contrast and increase the sharpening of the image, I'm able to follow that hand all the way up through my backswing, the same efficiency, if not even better, without any jitter. And as I come down through my swing, I'm able to follow my hands all the way across my full swing and all the way up until I reach my face. Now the reason why I end up losing the track at the top of my swing is because my facial skin tone is the same as the skin tone on my hands and on my forearms. So it's not going to pass through my head to the backside where my hands will continue, because it sees my forehead as the same as my hands. Now if I was wearing some sort of mask or something that would remove any skin from my face, with the prediction filter, because my hands are moving laterally at the top of my swing, it would continue with that path until it reached the backside of my head and found my forearms and then continued until the end of my swing. So as you can see, applying just simple contrast enhancement, I'm able to continue my swing even though it's the exact same video. So now for some of the results of this project. The main results were to determine if applying a linear prediction filter and a Gaussian kernel would improve the track while also improving the processing speed. So this is a quick example of the efficiency of the Kalman filter itself. This red window over here represents the track that I will be eventually getting to from the final mean shift vector. And as you can see, my hand is inside that window. This blue window represents the starting location, or where my hands were on the previous location. And this is an example of the non-contrast enhanced video. So you can see it's completely outside of the window. It's going to be completely lost. However, if I apply the Kalman filter, this green window represents the starting location after the Kalman filter has been applied. And I have some pixels on my hand over here, and that's how I eventually was able to shift over. So having no Kalman filter will completely lose the track, even though on this specific frame I was able to continue on. And some more, I have a couple more comparisons of where the efficiency of the Kalman filter itself. So during the code, I kept a counter running for every single frame of how many iterations were required to converge on the local mean when using a Gaussian kernel between a Kalman and non-Kalman filter. And as you can see, they're essentially the same. Out of 140 frames, there aren't too many deviations. There aren't too many times where I have less iterations because the starting location was that much better. However, if I repeated the process, but rather than saving off the number of iterations needed, instead save off the total time needed to process the speed, it's clear that adding the Kalman filter greatly increases the processing speed. This blue line represents the non-Kalman filtered time, and the green line represents the average of that amount of time needed to process each frame. The black line represents the Kalman filtered times, and the red represents the average. So as you can see, there's a difference between the non-Kalman to Kalman filtered algorithms. So while we are able to increase the productivity of the track itself and be able to track targets while they move behind trees, for example, as seen in the one car video, we're also decreasing the amount of speed needed to process each frame. Now, for this example, it may not be the most critical thing, but in real life situations where we're going to be tracking algorithms on an FPGA or some other processor and a large system, there's going to be other algorithms running on the FPGA itself, whether it's other image processing algorithms to improve the imagery for a pilot or some other features. So decreasing the speed per frame of just the track itself is a huge advantage. So in conclusion, I have proved that applying a Gaussian kernel greatly improves the mean shift algorithm efficiency when compared to a flat kernel. Unless you designate a specific point or only a couple pixels of the flat kernel, it's going to lose its track, which I have shown. However, with a Gaussian kernel, due to the math behind it, it does in fact stay with the target pretty well. Linear prediction filters also have been shown to decrease the time and number of iterations slightly needed to process each frame. So even though we're adding a couple extra steps and other code that we will need to implement every frame, it essentially decreases the amount of time still due to the impact of the prediction filter. For future research, we could look into, instead of using a linear prediction filter, using a quadratic filter or an adaptive prediction filter. These both will require more processing power needed due to more extensive calculations. However, should improve that starting location, especially the adaptive filter. For example, a golf ball. On start, once the ball is struck by the club, the ball is going to go from not moving to moving incredibly fast. If we use a linear prediction filter, we may not be able to follow the ball because it's not moving originally. However, if we use an adaptive filter, we are going to see that we went from not moving to moving very quickly, and the code essentially will adjust to this movement. Now, after the ball has landed on the ground and is just rolling, it'll then adjust down to potentially maybe a linear aspect again, where it'll require less processing speed because it's not as hard to predict the location. So for future research, I think this would be another great example. But for my research, just for proof of concept, applying a linear prediction filter does decrease the processing speed while increasing the efficiency as well. So this concludes my presentation. If you have any questions, feel free to comment on the video below. Thank you.